In Chapter 13, Part 2, I'm going to show you some sample IR spectra for different functional groups so you know what to look for when you encounter your first IR spectrum in lab next quarter. First of all, for my class, ignore the region that's below 1500. So ignore this region below 1500. This is a region of the spectrum that's usually difficult to interpret. It's also known as the fingerprint region. And there are some important peaks in this area of the spectrum, but we're not going to be talking about them. Alright, so this is a spectrum of a straight chain alkane, and one of the first things I do when I look at an IR spectrum is I draw a line that goes straight up through 3000. And the reason that I do that is I'm looking for peaks immediately on either side of 3000. If we are immediately to the right of 3000, I have sp3, carbon hydrogen. And certainly the straight chain alkane has many sp3 carbon hydrogen bonds. Immediately to the left of 3000 is sp2 carbon hydrogen, and you can see that I have no sp2 carbon hydrogen in this molecule. The other thing that we would expect in this molecule is carbon-carbon bonds, but the carbon-carbon bonds are in that fingerprint region that we're ignoring, so we're only looking at 1500 or above. Alright, so this would be an example of an alkene. Now this alkene is an unsymmetrical alkene, so although the carbon-carbon double bond is nonpolar, because it's unsymmetrical, we would expect to get a peak. It's going to be little, but we would certainly expect to get a peak, and that's what this is right here. This is in the double bond region, and this is the carbon-carbon double bond here for this alkene. Drawing our line up from 3000 again, you can see that we have peaks on either side of 3000. We have sp3, carbon hydrogen, and we have a little peak here for sp2 carbon hydrogen. So we have both in this molecule. And you'll also see here that we have these peaks right here at 1500. We're ignoring this whole region, so don't even need to look there at all. The next spectrum is an alkyne, and this is an unsymmetrical alkyne. It's also called a terminal alkyne, and because we have a terminal alkyne, so what that means is that we have a hydrogen on this end here, carbon hydrogen bond. So what we would expect for this molecule is that we would have an sp carbon hydrogen, and that's exactly where this should show up, sp carbon hydrogen. We also have our carbon-carbon triple bond. Remember, not a very polar bond, and so we expect a very small peak here, but this would be our carbon-carbon triple bond peak. And in this molecule we can still draw our line up from 3000, and we'll see that we have sp3 carbon hydrogen. But you can see that the region of the spectrum where we would have the sp2 carbon hydrogen right here, we don't have anything there. So let's label that. No sp2 carbon hydrogen in this molecule. Let's look at an alcohol. This is the classic appearance of an alcohol. We said in the IR chart that we can have a sharp sharp peak for the alcohol, or we can have a broad peak for the alcohol. This is more commonly what we see, and this is a very common shape for an alcohol here. So this is our OH stretch right here, so let's label that. This is our OH stretch for alcohol. We're still going to draw our line up from 3000. And as you can see, we have sp3 carbon hydrogen. We have no sp2 carbon hydrogen. And of course, easy to be able to tell that when we have the structure of the molecule drawn right in front of us. We're not always going to have that. We're rarely going to have that, but it's helpful to know what we're looking for in this IR spectrum. And again, the more complicated region below 1500 we are ignoring. Here's another example of an alcohol. And as you can see, we have a much bigger peak this time. That alcohol OH peak is pretty much the most predominant peak in this spectrum. This is our OH. If we draw our line up from 3000, for this particular example, you see we have peaks on either side. So there's our line up from 3000, and we have sp3 carbon hydrogen, and we have sp2 carbon hydrogen. We have both. The only other thing I want to point out in this molecule is this bumpiness here that is just below 2000, and that's peaks from the double bonds in the benzene ring. Sometimes those are prominent, sometimes they aren't very prominent, but they're, very much depends on the substitution pattern of the ring. So it tends to be more predominant when we have mono-substituted benzene ring. When we have di and tri-substituted, this may be less noticeable, but again, peaks are going to vary depending on the structure of the compound that you have. This is a classic appearance of a ketone. We're going to do our line up from 3000 like we have been doing here. And as you can see, we have sp3 carbon hydrogen only. We don't have any sp2 carbon hydrogen. And the most intense peak in the spectrum, and this is very common for a carbonyl, is this carbon-oxygen double bond from a ketone. How do we know it's from a ketone? We would need an actual peak value for this. Now, this particular IR spectrum doesn't really have a scale on the bottom that we can see, but on this particular instrument, it gives a peak printout for all the peaks, so we could see the exact peak that this is. And if you look at the peak printout, you can see this is exactly right where it's supposed to be at 1710 reciprocal centimeters for that ketone. And that's all we really need to get from that spectrum. So as you see, as you can kind of get an idea, we're looking for functional groups. We're also looking for what type of carbon-hydrogen bonds we have, whether we have sp carbon hydrogen, sp2, or sp3. That's very useful information. Here's another ketone that looks completely different. Once again, this carbonyl here. This carbonyl is the most predominant, most intense peak in the spectrum. That's the carbon-oxygen double bond from a ketone. But rather than 1710, when we look at the peak printout, we get 1680 reciprocal centimeters. And that's simply because this ketone is conjugated. Alright, so we've got the carbon-oxygen double bond here, single bond, double bond, single bond, double bond, single bond, double bond, single bond. We have alternating double bonds, so this is conjugated. And remember, we said when it's conjugated, it lowers by 30. So a regular ketone would be 1710. We drop by 30, and it goes to 1680. So this is conjugated ketone. As you can see from our structure, we also have both sp3 carbon hydrogen and sp2, and we really do have peaks on both sides of 3000. They're small, but they're there. So this right here would be sp3 carbon hydrogen, and immediately to the left would be sp2 carbon hydrogen. This is a classic appearance of a carboxylic acid, and looks totally different than an alcohol. And so what we notice is, when we talked about the oxygen-hydrogen bond from a carboxylic acid starts over here in the 3000s and extends all the way down into this region of the spectrum. So that's the very classic appearance of a carboxylic acid. So it doesn't look at all like an alcohol, because it just extends all the way into this range. And we would also look for, if we suspect a carboxylic acid, we would also look for the carbonyl of a carboxylic acid, and that would be right here. So remember, in a carboxylic acid we have a carbon-oxygen stretch, and we have an oxygen-hydrogen stretch. So this is the carbon-oxygen from carboxylic acid. So the peak printout gives us a peak value of 1710 reciprocal centimeters, which is exactly what we would expect for a carboxylic acid. And so this right here, this very large peak, is our oxygen-hydrogen stretch. Oxygen-hydrogen from carboxylic acid. And then, as you can see, we still have this sp3 carbon hydrogen, but it almost looks like it's hanging off, and it is. It's hanging off that oxygen hydrogen peak from the OH of the carboxylic acid, but this is still definitely our sp3 carbon hydrogen. All right, this is a classic spectrum of an amine. We have a primary amine here, so we have two nitrogen-hydrogen bonds. So we have two peaks or bands from two nitrogen-hydrogen bonds. So that tells us that we have a primary amine. We also have our peaks immediately to the right of 3000, so we'll draw our line up from 3000, and you can see we have sp3 carbon hydrogen here, and that's really all we need to get from the spectrum. Alright, so this is a little different. This is not an amine, it's an amide. And so what we will have is we will have our nitrogen hydrogen, and then we will also have our carbonyl. So these guys are two nitrogen-hydrogen bands from our amide, and then we have our carbonyl, and there's two unusual things about an amide, and one is that this is at a really low value here. So this is the carbon-oxygen from an amide. A typical amide would be 1650. This is actually lower by 30. So this is, if we look at the peak table, this would be at 1620 reciprocal centimeters. And that's because the amide is conjugated. So that lowers the value by 30. So once again, the conjugation, this carbon-oxygen double bond, single bond, double bond, single bond, double bond, single bond, double bond, single bond. So those are conjugated bonds. Let's also draw our line up from 3000 here. And sometimes it is a hard call to know what's going on here. I would not be able to tell if that had sp3 carbon hydrogen. It doesn't. We've got the structure of the molecule right here, but sometimes you can't tell when we have a peak that descends really low like this. So this would be our sp2 carbon hydrogen. And, you know, we notice some bumpiness here below 2000. Again, that's from the benzene ring here. Alright, so here's a nitrile. So we have a carbon-nitrogen triple bond. That is a polar bond. And so right here is our carbon-nitrogen triple bond. We also have our lineup from 3000. And as you can see, sometimes this is deceptive. So here we have sp3 carbon hydrogen, but not really able to tell. Do we have sp2 carbon hydrogen? So sometimes it's not as easy to tell. It certainly looks like there's something going on there, but it's very small. And so for a compound like this, you would need verification, so you would take an NMR and see what the NMR looks like and use the IR in conjunction with the NMR. We also see some bumpiness here below 2000. That again is the benzene ring. This one looks like it's a different pattern than the mono-substituted, and all the different substitution patterns have different patterns with them. But that's definitely peaks from the di-substituted benzene ring. Alright, and here we are at the last IR spectrum, and notice there's no structure drawn. So we're going to try to figure this one out ourselves. So we have C7. So giving you the molecular formula, C7H6O. Alright, and what we use with that molecular formula, that's going to tell us the atoms that are in the molecule. And we can also use that to determine units of unsaturation. So you'll want to take a look at the units of unsaturation podcast. We will also be talking about units of unsaturation on the last day of class. So if we want units of unsaturation, we ignore oxygen. So if saturated, this molecule would follow the rule CnH2n plus 2. Or with 7 carbons, C7H16. Alright, it is not C7H16, it is C7H6. So what we do is we take our 16 minus 6, and we see that it is short by 10 hydrogens, so therefore we have 5 unsaturations. Alright, so we have 7 carbons and 5 unsaturations. And what that usually means when you have a small number of carbons and a lot of unsaturations, that usually means that you have a benzene ring in your molecule. So that's what I'm thinking here. We have a benzene ring. If we draw a benzene ring, then that takes up 6 carbons, and we only have 1 more carbon here. So that's what we have so far just from our units of unsaturation for our molecular formula. So let's see what else we can find. I'm going to draw my line up from 3000 here. And it looks like I have peaks on either side. sp2 carbon hydrogen, and it's actually a little bit deceptive here. We definitely have sp2 carbon hydrogen, but it looks like we have sp3 carbon hydrogen, and we don't actually have that in our molecule, but it looks like we do. But what I do notice right here is these 2 peaks. We have one at 2700, and we have one at 2800. Does that ring a bell? That is the classic appearance of an aldehyde carbon-hydrogen bond. So it looks like that. That would be the classic appearance for the aldehyde carbon-hydrogen stretch. And so that's definitely, we definitely have that there. The only thing we're uncertain about is the sp3 carbon-hydrogen. So if we suspect we have an aldehyde, let's look at the carbonyl region of this spectrum. So we look here, and we definitely have a carbonyl. That's the most intense peak in this spectrum. We suspect an aldehyde. What is the value that we get here? This is actually 1695 reciprocal centimeters. If we look at our peak printout, 1695. A classic aldehyde would be 1725. We get this from our IR chart. Classic aldehyde, or typical aldehyde, would be 1725. This is lower by 30. Which suggests a conjugated aldehyde. So that's what we're going to think we have here. Certainly looking like a conjugated aldehyde here. All right, and so if we draw an aldehyde here, we've only got one carbon left. All right, so we've got our aldehyde, we've got our benzene ring. We've got 1, 2, 3, 4, 5 unsaturations, and that looks like that's what that compound is. And that is what that compound is. So the only problem here we have is this little thing right here where we weren't sure whether we had sp3 carbon hydrogen. And when that's the case, we would take a look at the NMR spectrum for this compound, and we would be able to tell right away.